Okay, welcome back. We're going to go ahead and go over the rest of the lab since I kind of ran out of time last time. Okay, welcome back. How's everyone doing?
Wow.
Good weekend?
Yeah.
Good weekend? All right. So we'll talk about the in-order pipeline homework, and then we're actually going to go through full slides explaining how each piece works. This should be a review from your undergrad, but I know that sometimes it can be a long time, so if you need to catch up, please come and talk to me or speak to me. All right, pipeline implementation. This, we're going to use the data path from Appendix A of the Patterson and Hennessy of the undergrad book, not necessarily of the graduate book. Now, the back of that book actually uses MIPS. Is it too small? Here, let me fix that for you. Back of that book uses MIPS, which is slightly different than what we're coming up with, but they are very, very similar. The implementation that the architecture I've put forth in this document is, I would say, a lot simpler than MIPS, so hopefully it'll be easier to implement. First off, big difference with MIPS, when you add to the PC counter, you always added 4 in MIPS because it was byte aligned. We are word aligned, so only add 1. The instruction bit fields have to be modified to suit what LC's instruction set is. MIPS is a little different. That'll become pretty obvious when you delve into it. The shift left 2 components not necessary since both offset for branches and PC are word addressing only. Again, really what all this is that MIPS was byte aligned, and since our processor is word aligned, a couple of things are actually a lot easier. The main difference between this assignment and the pipeline done in the book is that we will add a pipeline register after write back. So you can call it the write back end pipeline register. This will also be useful for simplifying data forwarding when we talk about forwarding. Remember forwarding that? No? Yes? Okay. I highly recommend you follow the textbook as closely and you use the MIPS clocking scheme. aka register file and memory writes require data to be present for the whole cycle. Okay. Don't I give you the code for this? Okay, good, I do. Oh. Memory. The way a lot of simulators work that's a lot easy, or I say it's easier to do it this way, is you keep 2 full memories. One is the previous cycle and the other one is the current cycle you're working on. That way you can always reference what the beginning values were as you populate what the next values are supposed to be. Does that make sense? This is probably the easiest way to do this type of simulation when it's cycle accurate. You have 2 memories. One, of course, represents the previous cycle, and the next one represents your current cycle. And so you're going to calculate everything from the previous cycle, store it in the new cycle, and then when you're done calculating or simulating that cycle, you simply copy it to the old one and start again. All right? Does that make some sense?
Yeah. Just keeping your state.
Yeah, keeping the state. Always keep this previous state, and then you're calculating the current state. When you're done calculating the current, you copy it over to the previous, go to the next cycle. That'll probably be the easiest way to do this simulator, and the way I recommend. All right. To simplify this project and make the output formats uniform, we can use the following structures to hold pipeline registers. So here I've defined at least some of the code in C for you, this is in C. You can convert it to whatever language you want, as long as it's not JavaScript. Memory, remember we have 64 kilobytes of, not kilobytes, but kilo words. 8 registers in our architecture. And then I've gone ahead and defined what the different instructions are that are possible. And I went ahead and fully defined what a no-op instruction looks like. So if you need to populate or look at an example, there you go. Type def struct. If you haven't done this before, you can just think of this as a class. It's a record. Everything inside of it, since it's a struct, is public, and you can't put functions in it. So it's really just collecting data together. So if you recall correctly, the fetch and decode between, you just store the instruction in PC+1, and then decode to execute. Again, more information, and here are the different pipeline registers. I'm going to go through this in the presentation after this, so a lot of this should make a little more sense, but I have typed it out, at least the recommendation I would have. And notice that at the very end we would have, or at the end you would have your write back. When you did undergrad, did you do the 5-stage in order pipeline?
I don't remember.
You don't remember? Okay, so
That's-
between
that was
each
a long time
each
ago.
stage you need to store what the state is.
Right.
So these are just the registers to store the state.
Oh, okay.
That's all it is. And then, of course, the state structure for this is your whole simulation, your PC counter, your instruction memory, data memory, your registers, amount of memory, and then here are your register file or your pipeline registers between each stage, and then of course how many cycles have you done. So here I've written out the state for you, which is probably half the battle. Not at all. No?
Yep.
Okay. All right, so your task is to write a cycle-accurate simulator for the little computer. At the start of the program, initialize the PC at all registers to 0. Make sure you do that, especially if you're coding in C, because C will not do that for you. Initialize the instruction field and all pipeline registers to the no-op instruction, which I've already given you, because no-op tells you not to do anything, so that makes it easy. The run function, you'll probably have this somewhere. Do I actually give you a full listing of the code, or do I...
You give us like the insert your stages here thing.
Oh,
right
okay,
there.
cool, sweet. All right. Isn't that nice of me? All right, the run will be a loop where each iteration through the loop executes one cycle. So it's just going to keep going through a loop, executing one cycle at a time. At the beginning, print the complete state. You may use the print state function of this handout. So, aka copy and paste it, please. In the body of the loop, you'll figure out what the new state should be, and then at the end of the cycle, and then what everything should be at the end of the cycle. Conceptually, all stages of the pipeline compute their new state simultaneously, but since C doesn't do everything simultaneously, that's why I'm saying you should have 2 states, the previous and the next, and then you basically copy everything over. Let's see. Each stage of the pipeline will modify the new state variable using the current value. So, for example, new state, and you want to update the instruction, it would be of the old state. Here I just called it state. Dot instruction, and that would transfer it to the new state. And then, of course, at the end, you just have state equals new state to copy it all over. And you just keep on going from there. To keep it simple, and just make sure you're clear in your loop, new state is only the target of the assignment, aka you should always have new state equals something from state at pretty much all the time, except for at the very end where you copy, the new state over to state. All right, keeping it simple. Your simulator must be pipelined. So this is going to be the standard 5-stage classic in order pipeline. This means that work of carrying out an instruction should be done in different stages, so different cycles, just like in the textbook. The execution of multiple instructions should be overlapped. So while it's going down the stage, other instructions are coming down the pipeline. The ID stage should be the only stage that reads from the register file. If you try and do this differently, you will fail some test cases. Make sure that the ID, the decode stage, is the only one that reads from the register file. Here's an example main run loop. While 1, print the state. If the new opcode is not 0, or is not, if it's halt, say we're halting and then get out. Notice that I'm halting once that instruction gets to the very end. New state equals the state, increase the cycles, compute the IF stage, compute the decode stage, the execute stage, mem stage, write back, and then at the very end is where you copy the new state over the old state. Make sense what the overall,
So
design of this would be?
that's your 5 stages.
Yeah, there's your 5 stages right there. Obviously, you write the code for this. Obviously, yes. We're doing good so far? Great. Halting. At what point does the computer know to halt? All right, I kind of gave that away. It's incorrect to halt as soon as the halt instruction is fetched because of an earlier branch was taken. if an earlier branch was taken, the halt instruction would have not branched around. Do you understand what I'm saying here? Do you remember
I think so.
with branch prediction, if you mispredict the branch, then you're starting to execute instructions that you shouldn't be.
Yeah.
And if one of those happen to be the halt instruction and you decide to halt early in the pipeline, then you might be halting too early. So that's why you usually halt it when it comes into the mem write back register. All right, I suggest at the beginning, your beginning implementation, you assume no hazards, because it's going to take you a while to get just that correct. So when you write your test programs, make sure there's no data hazards or branching hazards. And we'll go over that again today. But first, implement it without hazards. And make sure you code your test examples with no hazards. Then go in and actually account for the different data hazards. So you can use data forwarding to resolve most hazards. We'll go into a lot of these, like the ALU should be able to take its inputs from any pipeline register. But you will need to stall for one type of data hazard, a load word followed by instruction that uses that register being loaded, because it hasn't gotten back from memory yet. So you still need to implement at least one stall.
So that one's always going to stall with this project.
No, only a load word followed by an instruction that requires what's being loaded. That's the only time you stall.
Okay.
Because if it's a load word, you have some other instruction, and then an instruction that uses that load word, you're okay because you have that one cycle delay. Control hazards. We will be doing a branch predictor for this course. You did not simulate one in my previous course, so this will be a little new. There'll be a 4-entry pattern history table containing 2-bit state machine. We'll get into that. Initial state will be weakly not taken, and you will also implement a 4-entry branch target buffer organized as a fully associated cache with FIFO replacement. Yep, we will get into that. You got all that? Okay. All right. You will implement a branch predictor, and of course you're going to want to take everything from the branch predictor. When a branch actually comes up, you will decide whether it's taken or not taken, and then go from there. All right, output, cycle time, number of instructions fetched, retired, which are the number of instructions that are actually completed, any branches that were executed, aka resolved, you actually went to the branch, and then number of branches incorrectly predicted.
Minus 5 points for each one.
It should be pretty simple to run. See whatever your program is, and then, whatever you compile your program, I pass it the machine code file, and then the output should just be printed out. All right, now test cases. So this is going to be a little different. This is graduate school. You are 100% responsible for your test cases, and you have to convince me that your simulator is sufficiently tested with your test cases. So I'm grading basically your test cases is what I'm really grading here, along with maybe reading your code. But you need to explain to me why your test cases are sufficient, and give me which is common practice. You need a comprehensive test suite. You should have short assembly language programs that, after being assembled in machine code, serve as input to the simulator. You will submit the suite of test cases together with your simulator, and we will grade your test suite accordingly how thoroughly it exercises the pipeline simulator. So I'm going to look at your test cases and see if it actually thoroughly tests everything. And I'll probably take your test cases, run through mine, just to make sure they're correct.
So the test cases, we just need like assembly, like we just need to read little things like that for it. Okay.
Lots of them. And again, well, not again. At the end, document describing overall operation of your simulator, discussion of how each test case demonstrates correct operation of some portion of your pipeline implementation. Should include executing instructions, forwarding data hazards, and operations of both the BTB and the G-share predictor, aka your branch predictor. All right, you will submit via GitHub. If you've not done so already, create an account. Make sure you fork the repository and upload to the repository. Hopefully we've done that here. Those of you online, make sure you get going. Have you forked it yet? You don't know? Okay. And here's the code for the print state that you can use, along with the code up there that I'll print it out for you. I don't need to go over this. Maybe I do. Okay, here we go. Here's some sample assembly. Load word, base 0 into register 1, data 1, which is this label of 1, 2, 3, 4, 5. Note especially how halt is done. It's done right afterwards. The add 0, 0 after the halt are from the memory location after the halt, which were initialized to 0. So do you know where add 0, 0, 1, 2, 3, 4, 5 came from? That's a good question. So when you assemble this program, this is what you're going to get out.
Is that in decimals?
Yeah, these are in decimals.
Okay.
Instruction memory is going to look like this. Why is the last one add 0, 0, 1, 2, 3, 4, 5? Your assembly is up here. Here's your assembly. Why is that last instruction add 0, 0, 1, 2, 3, 4, 5? Come on, man. You got this.
It was a long time ago. It was like 5 months ago.
What is the add?
Where'd the add come from?
Is that just filling in because of the size of that location? 1, 2, 3, 4, 5. What's the size of that?
So these are all 4 bytes? Yeah, 4 bytes. So remember,
Where's that?
data.fill is just going to put 1, 2, 3, 4, 5 at the very end of those 4 bytes, and the previous is just going to be a bunch of zeros, which happens to map to add 0, 0 here. So that's where that add comes from. Does that make some sense?
Say that one more time, please.
So remember, when your program is assembled, it's going to have the load word followed by a halt instruction followed by data of 4 bytes that have the data 1, 2, 3, 4, 5. Instruction memory is going to read everything from that assembler and put it into instruction memory. So you got load word and halt corresponding to these two guys up here, but you have a third word, which is just this fill of 1, 2, 3, 4, 5, and that is why it's down here of add 0, 0, 1, 2, 3, or 5, because that's just happens to be what it maps to. Notice that data memory down here is what you're looking for because the 1, 2, 3, 4, 5 is a data mem sub 2. Your register should be 0, no op, PC plus 1. It can be a different value than that. I'll be okay with that. Notice that read reg, let's see, before cycle 0, 6, 1. Really, these don't matter. These do not matter because they're pretty much zeroed out. They're all no ops. When cycle 1 begins, notice that instruction fetch has the load word. Everyone else still has a no op. Cycle 2, that's when instruction fetch has the halt and the load word is in the basically the execute stage. I mean, the decode stage. Whew, that was bad. Then the next cycle, the add is in the fetch because that's where it's coming from, because it's actually the data, even though it's not going to execute that. You have the halt instruction in decode, and then you have the load word and execute. And next, afterwards, you just keep loading basically all zeros, which is add 0, 0, 0. So those two are in there, but these are superfluous instructions. We have the halt, we have the load word, and we need to write data. And notice that in the next one's where we finally write to the register file, and the load word's in the right back end. And then you halt because the halt instruction's in memory write back, or in memory stage. Okay? Does that example make some sense? Any questions about this before I do a full review of the in-order pipeline? Nope.